Hello and welcome back to the Biochemistry for Health Sciences channel. Isoelectric point is a very important characteristic of chemicals such as proteins. Before we talk about the importance of isoelectric point and its applications, which we'll do in a future video, in today's video we shall look at how we can determine the isoelectric point of a chemical, such as an amino acid or a protein. In previous videos, we mentioned that biomolecules, such as amino acids, proteins, fatty acids, and then we have drugs. Biomolecules and drugs often tend to have functional groups which can exist either as their protonated form or their unprotonated form. So common functional groups that can exist as protonated or unprotonated include amines, where the protonated form is positively charged, the unprotonated form has no charge or neutral. Carboxyls, where the protonated form has no charge, while the unprotonated form has a negative charge. Sulfhydryl, protonated has no charge, unprotonated has a negative charge. Same thing with hydroxyl, protonated has no charge, and unprotonated has a negative charge. We also discussed in previous videos that the predominant form of the functional group, whether it's protonated or unprotonated, depends on the pKa of the functional group as well as the pH of the medium. So for example, in the drug amphetamine, which has an amine group, the protonated form you can see is positively charged, while the unprotonated form is neutral. On the other hand, aspirin, the protonated form is neutral, as a carboxyl, it is neutral. The unprotonated form is negatively charged. So in these two examples, we do not use isoelectric points because the molecule exists. For example, amphetamine exists only as a positive or neutral. There is no negative form of amphetamine. Similarly, carboxyl exists, the carboxyl of aspirin. Aspirin has only carboxyl that then exists either as neutral or as negatively charged. There is no positive charge structure in aspirin. So in these two cases, we do not use the concept of isoelectric point. However, in chemicals such as amino acids and proteins, the same molecule has functional groups that can give you a positive charge as well as a negative charge. So these kinds of molecules where you have functional groups that can give you positive as well as negative charges, we can describe their isoelectric point. So in case of glycine that has two pKs, all we have to do to determine the isoelectric point or pI of glycine is to take the average of these two pKs, 2.3 plus 9.7, divided by 2, that gives you an isoelectric point of 6.0. So the pI of glycine is 6.0, which means that if you take glycine and place it in a medium with a pH exactly equal to 6.0, which is the pI of glycine, then all 100% of glycine molecules will exist in this form, this structure 2, where you can see a positive charge neutralizes a negative charge. So the net charge of glycine is 0. So the isoelectric point is the pH at which the net charge of the molecule is 0. What if a chemical has more than 2 pK values? So let's look at an example to determine the pI of lysine. Lysine has 3 pK values, 2.2 for this carboxyl group, 9.1 for this amine group, 10.5 for this amine group. So one way of determining the pI is to first write the structure where all the groups are protonated. All the groups that have pKs are protonated. And once you have this group, which is structure 1, then look at the group that has the lowest pK, which is this group here, carboxyl. Let it lose its proton. So this will be unprotonated. And then go to the next lowest pK, which is for this amine group here, 9.1, and make it lose its proton to make it unprotonated. That gives you structure 3. And then finally, the next lowest pK is 10.5, which is for this amine group. Let it lose its proton, and that will give you structure 4. So you can see a chemical that has 3 pKa values has 4 structures. So now you look at the structure that gives you a net charge of 0, and we see that in structure 3 because a negative carboxyl neutralizes a positive amine. So now we simply take the pKs on either side of this structure 3 that has a net charge of 0, 9.1 plus 10.5, take the average of the two divided by 2, and you have your pI of lysine, which is 9.8. So this means if I place lysine at pH 9.8, which is the pI of lysine, 100% of all lysine molecules will have structure 3, where the net charge is 0. So writing all these structures, 1, 2, 3, 4 in case of lysine, and then determining the pI is quite a long and tedious method. There's a simpler way of doing this. All we have to do is write the structure where every group is protonated first. Okay, so just look at only the groups that have pK values. You can just ignore the rest of this structure. Okay, so this is your structure number 1. Once you write the structure number 1 where everything is protonated, calculate its net charge. So you can see that there's 1 positive charge here, 1 positive charge here. This is neutral, 0 charge. So the net charge is plus 2. Now all we have to do is just use the same pK values and change the next structure. Will have a net charge of plus 1, as you can see. And then the next pK, 9.1, will give you a structure that has a net charge of 0, as you can see there. And then the last pK, 10.5, will give you a charge of minus 1. So you can see the charge decreases by 1 as we go from left to right. So now all we have to do is identify the 0 charge, look at the 2 pKs on either side, 9.1 and 10.5, and do exactly the same thing. Take the average of the two, and you get your isoelectric point of lysine in this case, which is 9.8. Here's another example. Let's determine the pI of another amino acid, glutamic acid, which has 3 pK values for this carboxyl, 2.2, 9.7 for this amine, 4.3 for this carboxyl. So once again, the simplest way of doing it is simply write the structure where everything is protonated. This is protonated, this is protonated, this is protonated. Calculate the charge. The net charge is plus 1 because that's the only charge available in structure 1. And once you have plus 1, now you simply go with the lowest pK, 2.2. The next structure will have a charge of 0. then 4.3 will have a charge of -1, and then 9.7 will have a charge of -2. And now you simply take the 0, the structure that has a charge of 0, take the pK values on either side, which is 2.2 plus 4.3, average them, and you get your PI, which is 3.3. This means at pH 3.3, 100% of all glutamic acid molecules will exist as structure number 2, where the net charge is 0. What if we have a more complex structure? For example, this polypeptide where you have 1 pK, 2 pKs, 3 pKs, 4 pKs, 5 pKs, 6 pKs. Okay, so clearly writing all the structures out will be a very long and tedious method. So let's try to determine the PI, isoelectric point, of this small polypeptide, this small protein. So the first thing we do is we take this structure and make every group that has a pK protonated. So we can start anywhere, but let's start with, let's say, this amine group here. Let's protonate it, and when it's protonated, becomes positively charged. This amine, when we protonate it, becomes positively charged. This amine, when we protonate it, becomes positively charged. Carboxyl, when we protonate it, you get COOH, which is the correct way it's written. Hydroxyl, when you protonate it, that's the way it is, 0 charge. Sulfhydryl, when you protonate it, that's correct, acid, that's the structure you get. So this is the protonated form of this polypeptide chain, where every group is protonated. And when you look at the charges, there's 1 positive, 2 positive, 3 positives. So that's the first structure that has a net charge of +3. So once you know the net charge of the structure that is fully protonated, then we simply start with the lowest pK. It's 1.8. That will give you another structure which has a net charge of +2. Then the next lowest pK is 6. 6 will give you a structure +1. Next lowest pK is 8.4. That will give you a structure of 0. Then after the next lowest pK, 9.3, you get a structure, net charge of -1, and so on. 9.9, you'll get the structure with net charge of -2, and then the next lowest pK, 10.5, you will get a structure with a net charge of -3. So you can see this protein, which has 1, 2, 3, 4, 5, 6 pK values. You have 1, 2, 3, 4, 5, 6, 7 possible structures. So now to find the PI, we simply take the structure that has a net charge of 0, take the pK values on either side of it, that's 8.4 plus 9.3, take the average of that, and you get a PI of 8.9 for this polypeptide chain. So this means that if I take this polypeptide chain and place it in a pH exactly 8.9, 100% of all these polypeptide structures will have a structure with a net charge of 0. There's another important concept I want you to look at in this example. So here's a polypeptide chain, but this could very well be a very long, complex protein. What you see here is we calculated the PI is 8.9, so it's more than 7. And the reason for that is you can see there are more amines, basic amino acids. So when you have more basic amino acids, especially lysine and arginine, it tends to increase the pi more than 7. So in this case, 8.9. If we had more acidic amino acids in the polypeptide chain or the protein, then the pi would be more towards the acidic side, less than 7. So if a protein had more basic amino acids, then you would have a higher pi. And if the protein had more acidic amino acids, you would have a lower pi of that protein. And we'll see this in a future video. So this is one way of determining the pi or isoelectric point of a chemical such as an amino acid or protein. Now this is only possible if we know all the pK values of all the groups that can ionize in the protein. However, this is not possible, not easy to know, because the pK values, as we mentioned in a previous video, depends on the environment of the functional group. And in a protein that is folded, if an amine is in this environment, we'll have a different pK. If the same amine is in another environment, it will have a different pK. So these are just calculated values. These are theoretical pi values. There is a actual practical way of determining the pi or the isoelectric point of a protein, and that uses a technique, an electrophoresis technique, that we call isoelectric focusing, or IEF. So IEF is a type of electrophoresis technique. So electrophoresis is a technique by which any biomolecule that has a net charge, whether it's negative or positive, it doesn't matter. Let's say if it was negative, then when we apply that biomolecule on the top of a gel, that biomolecule will travel towards the positive pole, which in electrophoresis is called the anode. Now, if the biomolecule had a net positive charge, then we would simply remove this, make this the cathode, negative. Okay, so the positive will go towards the negative in this case. So in isoelectric focusing, the top of the gel is a weak sodium hydroxide solution that has a very high pH. The bottom of the gel is immersed in a weak acid solution which has a very low pH. Also in isoelectric focusing, we use special chemicals called ampholites. These ampholites will be found in this gel. Let's say we use an ampholite that will give you a gradient pH 3 to 12. So what will happen is, since sodium hydroxide is on the top, we will have a pH of 12 on the top of the gel, and then it will slowly go down, 11, 10, 9, 8, 7, 6, and so on, and the bottom of the gel will be pH 3. Now let's say we apply a protein on the top of the gel. Let's say this protein is over-albumin. Okay, over-albumin that has a pi of 4.6. So since this over-albumin is seeing sodium hydroxide, it will have, that's a very high pH, right? So all the carboxyls in the over-albumin will be CO minus. Unprotonated, the amine would be NH2. If it has any sulfhydryl, it will be S minus. If it has any hydroxyl, it will be O minus. So you can see the net charge of proteins when they are in very high pH will be net negative. So when we turn on the voltage, these over-albumin will start migrating towards the positive pole or the anode. As long as it has this net negative charge, it will keep on doing that. It will keep on migrating and migrating. But somewhere in the gel is a pH 4.6. So somewhere here is a pH 4.6, which is exactly equal to the pI of overalbumin. So once the overalbumin reaches pH 4.6 right here, now it will have a net charge of 0, which means it's not going to migrate anymore. So it will simply stay here. And not only that, when the protein has a net charge of 0, it's not very soluble anymore in water, and so it might even precipitate in a gel, forming this line here. So this band here is the band for overalbumin. So in this way, if you have a mixture of standard proteins whose pI we know, you can see they will be separated. Overalbumin with 4.6 will be here. Carbonic anhydrase 5.4 will be here. 7.0 is myoglobin, would be this band. 7.1 is hemoglobin. Cytochrome C is 10.6, very high pI. And histone, another very basic protein, is a very high pI of 11.0. So you can see all the proteins that have a higher pI will be facing the sodium hydroxide side, while the proteins with lower pIs will be facing the phosphoric acid side. So this is how your standard proteins will be separated on an IEF gel. Now the unknown protein will also travel in the gel, and when it reaches the pH which is equal to the pI of the unknown protein, that protein is going to not migrate anymore, and it will simply precipitate in the gel. So you can get an idea of this, of the pI. You can see the pI of the unknown protein is somewhere between 5.4 and 7.0. To be more precise, you could determine the migration distance of the standard proteins. You can determine the migration distance D and plot the migration distance with the pI of the standard protein and get some sort of a calibration curve, and then you can find the migration distance of your unknown protein, and from that migration distance you can extrapolate and find out the pI of your unknown protein. So these are the two ways by which you can calculate the pI of a given protein. One is theoretical by calculations that requires that we know the pK values of all the ionizable groups in the protein, which is very difficult in many cases. The second, more reliable and better way of determining the pI is using isoelectric focusing. So that is all for now in this video. In the next video, we shall look at the applications, the importance of pI in biomedical sciences.